All right, welcome to lecture 10.1, covering non-right triangles and the law of sines. So up until now, all of the trigonometry that we've been doing has been based on right triangles and how those fit into the unit circle. And so this last bit of information is about, okay, well, what do we do when we have a triangle that we want to solve and it's not a right triangle? So that's what we're going to be studying in 10.1 and 10.2. And then 10.3 is a topic that kind of skews away from everything we've really studied this semester and talks about polar coordinates. So we'll go ahead and get moving on this non-right triangle stuff. Okay, so the first thing we run across is just a description of what an oblique triangle is. An oblique triangle is just a triangle that's not a right triangle. So these three types of oblique triangles are what we're going to use the law of sines to solve. And remember, let me just remind you what solving a triangle involves. It means you are able to list all three sides, the length of all three sides, and the measurement of all three angles, interior angles, that is, on the triangle. So the first case that we will look at is what we call an angle-side-angle triangle. So that's when you're given one angle, you're given the inclusive side between another angle. So angle, side, angle. We also have angle, angle, side. So here's one angle that we know, another angle that we know, and then that side that follows. And you know, it could have been this side that we have. It's just stating that it's not flanked between the two angles we know. The one above, the angle side angle, is the triangle where that side is flanked by two known angles there. And then we have the third case, and they call it side-side angle, and I'm actually going to change that around so that it sticks in your mind a little bit better as an angle side-side. So the ass triangle. This one is an ambiguous case, and we have to look a little further into the structure of the triangle to be able to solve it. Okay, cool. I'm glad it makes sense to you now, Trevor. For those of you that can't see the chat window and are watching the video on MP4, Trevor says, oh, now the opening picture makes sense. He's talking about the meme that I put on the first page. So here's the angle side. So we have an angle and then two following sides after that we know. And I'm just going to put a star by this one because it is a special case type situation that we deal with there. So let's go ahead and move forward and look and see how the knowledge that we have already built this semester is going to help us figure out the law of sines that we can use to solve these three types of triangles. Okay, so here we have pictured an oblique triangle. And what we have done is dropped a height down from one vertex of the triangle. And we know from our previous experience with geometry, really, that when we drop a height down, it actually forms a 90-degree angle. So what we've actually formed here is two right triangles. expressing, you know, the sharing a common side that is not the hypotenuse of the triangle. So sides A and B end up being the two hypotenuse for that triangle. Ken, Ken, I was about to check you in, but you've already met your two study groups after midterm requirements. So, all right. So, what we start out with is pointing out something that we already know, and that is the sine of an angle. And we'll just start with angle alpha here. The sine of any angle, and we'll just call it alpha there, is equal to it's its opposite over its hypotenuse. So in this particular right triangle to the left, that's going to be side H, which is the height of my oblique triangle, divided by side B. So that's opposite over hypotenuse for that particular triangle to the left. And if I solve for the height in this particular equation, I can get an expression for it. So what I'm going to do is come here and I'm going to multiply both sides by B to get that out of the denominator right there. And now I have a very simple expression that represents the height of an oblique triangle. I get the height is equal to B times the sine of alpha. And remember, my angle alpha, the side that's opposite that is my side A. My angle beta, the side opposite is side B, and then I've got gamma up here that is opposite side C there. So we have an expression for the height as being B sine of alpha there. Well, if we go to the right, the triangle, the right triangle that's on the right that has this angle beta, let me get a different color here to work with this triangle. So we have angle beta right here. If I do this same sort of expression and find that expression for H using the other triangle, I will have the sine of beta is equal to its opposite, which is H, over its hypotenuse, A. And if I want to solve for height there, I do the same thing. I'm going to multiply both sides by that denominator. In this case, it's A. And here I get, okay, well, I have another expression for my height now. Height is equal to A times the sine of angle beta. Now, I've got two expressions that are both expressing the height of that oblique triangle. And since they're both equal to the height, I can set those expressions equal to each other because they're representing the same thing. So I can now say, well, B times the sine of alpha has to be equal to A times the sine of beta. And I can come in here and I can divide both sides by A and by B. This is just to get the same side with its corresponding angle. And here my B's divide out, here my A's divide out, and I get the relationship that the sine of alpha divided by its corresponding side is equal to the sine of beta divided by its corresponding side. And we could go through this argument again, and we would find out that we can also set up the same relationship for angle gamma and say that's got to be equal to the sine of gamma divided by side C. This right here is the law of sines. So you can use any two of the sine of that angle divided by the corresponding side and set up a proportion that will move you forward in solving for these triangles. Are there any questions so far? It's pretty straightforward at this point, I think. Looks like everybody's okay so far. All right. So let's see how we can use this. So we've got our law of sines right here, and we have two versions of it. You can either have the sine of the angle over the corresponding side, or you can have the corresponding side divided by the sine of the angle. It doesn't matter as long as they're set up proportionally like that. Okay, I tend to always do the angle on top. I don't know why, that's just the way I always do it, but you can certainly use either version that suits you. Okay, so we have a triangle here. It is oblique. We have a situation that is a angle side. So this is an angle side triangle because I know this angle here, I know this angle here, and then I know the side there. So I've got an angle side triangle, so I know that I can use the law of sines to end up solving this triangle. Well, I'm going to work with the easiest thing to solve for first. Since I've been given two angles of the triangle, I know what the third angle will be. All I have to do is take the sum of the interior angles of any triangle, which is 180, and subtract the other two angles from it. And I end up getting that this missing angle beta is actually equal to 100 degrees. Okay, so that was kind of a gimme there. That was an easy one. Now we can use the law of sines to bring in the side lengths to set up those proportions and solve for the other missing side lengths. So let me just point out the one relationship that you have set up is, oops, I drew straight through that 50 degrees there. Okay. So you know that angle alpha is equal to 50 degrees. And you know the side opposite angle alpha, so that's side A there, is of length 10. Now, let me caution you, all of these problems in this section, you are given the angles in degrees. So make sure that your calculator is set in degree mode and not radians for this section. So be very careful with that. Okay, so I know that the sine of 50 degrees divided by 10 has to be equal to, well, I can choose to start with either angle beta or angle gamma. I'll start with gamma because that was given to us. And so we're going to solve for side C first. So that's got to be equal to the sine of 30 degrees divided by side length C, which is what I'm solving for. So I simply get C out of that denominator. Well, actually, I take that back. You know, I can make it much easier on myself and cross multiply here. Now let me caution you. Cross multiplication only happens across an equal sign. This is the only time you can cross multiply is when you have a proportion set up, and a proportion is some fraction equaling another fraction. The only time you cross multiply. And all cross multiplication is multiplying by the denominators on both sides. It's just done all in one step. So when I cross multiply, I end up getting C times the sine of 50 degrees equals 10 times the sine of 30 degrees. And then all I have to do is divide the sine of 50 degrees off of both sides. And I get that C is equal to that expression on the right-hand side, but I'm ready to put it into my calculator. So let me show you how I put this thing into my calculator. I'm going to write it out because I used an extra set of parentheses just to be on the safe side. So I put this into my calculator by starting with a set of parentheses to hold that entire expression in the numerator. And I put 10 sine, it opens a parenthesis for the sine, 30, I closed my sine, closed my numerator, divided that by sine, it opens a parenthesis, 50, and closed that sign off. That's what I put into my calculator. And when I put that in, I find that C is approximately 6.5 units. So now I know that my side C is equal to 6.5. All I have left to solve for is side B. So I'm going to do the same thing I just did, except I'm now going to use side B and the sine of 100 degrees. So I have that same proportion set up. The sine of 50 degrees over 10 has to be equal to the sine of 100 degrees over side B. Multiply across, so cross multiply. And when I do that, I get B times the sine of 50 degrees is equal to 10 times the sine of 100 degrees. Divide both sides by the sine of 50 degrees. And that expression on the right-hand side is what you put into your calculator. Y'all give it a try. Try putting that thing into your calculator right now. I'll give you a moment. And when you get your answer for the length of side B, round it to the 10th place and please type it into the chat window. I want to make sure that you can put this into your calculator properly. Okay, thank you, Trevor. I'll pause the recording while we're doing this so that it doesn't make the video go longer. All right, so everyone came up with 12.9, and sure enough, when I put it into my calculator, I get that side B is equivalent to, or approximately rather, 12.9. So our triangle's solved. We've got all the angles and we've got all the sides. Is everybody okay with this? Give me a green check if this was good for you and made sense. Or a red X if it didn't. And ask a question if you have one, please. Okay, it looks like everybody's good to go. Awesome. All right, so we have another case here. This time we've got angle, side, angle. We've got this angle here, we've got this side, and we've got this angle here. So this is an angle, side, angle triangle. All right, so we're going to go through the same process of setting up the relationship that we already know. And to do that, since all we have is side B, but we don't have angle beta, we need to figure out angle beta first. So 180 minus 98 minus 43 tells us that angle beta is equal to 39 degrees. Okay, so now we know our third angle there. And we just need to use our law of sines using angle beta in side B and set up those two other proportions to get side A and side C. So we get the sine of 39 degrees over 22 has to be equal to the sine of 98 degrees divided by side A. And I'm just going to cross multiply. So A times the sine of 39 degrees has to equal 22 times the sine of 98 degrees. Going to divide the sine of 39 degrees off of both sides. And when I put that expression on the right-hand side into my calculator, I get that A is approximately 34.6 units. So this A is approximately 34.6. And now I do the same thing for side C. So the sine of 39 degrees divided by 22 has to be equal to the sine of 43 degrees divided by side C. I cross multiply. C times the sine of 39 degrees equals 22 times the sine of 43 degrees. I come in and divide the sine of 39 degrees off of both sides. And I get, when I put that into my calculator, C is approximately 23.8. So triangle is solved. We're ready to move forward. Now we get to the tricky one, the ass triangle, the angle side. And what your book tells you is that with these types of triangles, your solution may not be as straightforward as the other two types of triangles. And in some cases, more than one triangle might satisfy the given measurements for the triangle. So we call these the ambiguous case. So triangles classified as SSA or ASS, where we know two side lengths and the non-included angle. It can result in one of these four situations here. If one of the sides if the side that we've been given a measurement of that is opposite of an angle that we know is less than the height of the triangle, then no triangle is possible. And we'll end up seeing a case like that. If the height of the triangle is equal to that side that we know, that's opposite the angle we know, then we're dealing with a right triangle. Now here's the one that gets tricky. When we drop the height down, if our side A is longer than that height we drop down, and you can see if I drop that plumb line straight down, that's going to create those right angles. So if I create a side that is either to the left of that plumb line or to the right, these side A's are going to be longer than the height that has been dropped down. And these sides are equal. So this creates an isosceles triangle right there. And what we know about isosceles triangles is that these two angles here are also equal. So when this occurs, you don't know if it was this triangle that created the situation, or it may have been this triangle that created the situation. So you've got two cases. And then we have the case where our side A is greater than or equal to our side B, and that just gives us one. This is the ambiguous case. You're not really sure. Actually, all of these are represented by the ambiguous case. Oh, isosceles triangle. That's what you were asking, Ken, right? You were asking about the, okay. An isosceles triangle is just any triangle that has only two sides that are equal. If all three sides are equal, that's an equilateral triangle. Two sides equal is an isosceles triangle, and whenever you have an isosceles triangle, the two angles at the base of those two sides are always equivalent. Okay, great. Yeah, that's old school geometry for you. We're really pulling it out tonight. Okay, let's look through a couple of cases that are ambiguous. And we're actually going to start with one of these two triangle cases. So here we are. We have this is an angle side. We know this angle 35 degrees, and we know side 8, and we know side 6. So if I drop a height down for this triangle, the height would live right here. It always drops perpendicularly down. So just from looking at that, we can see that that side 6 is actually going to be longer than the height of the triangle, which means I could have the case here that could be the triangle that I am trying to solve for. So what we end up doing with this case is solving two triangles. So what we're going to need to solve for, let me just pull these triangles out and make them different colors. We have this case, the first one that was drawn for us. We know that this is 6, we know that this is 8, and we know that this is 35 degrees. And we've got angle gamma here, and we've got angle beta here. So this is angle alpha. We also have this case. So we still have angle alpha here that's 35 degrees. Now we have an angle beta prime. We've got a second angle beta there. We know that this side is 6. We know that this side is 8. We have a new angle, though, at the top that incorporates the top of those two triangles right there. So we'll call this gamma prime. So those are the two triangles that we have to end up solving for. All right. So the first thing that I ended up doing was figuring out what angle beta actually is. So I started out with the law of sines because I know, let me point out what I know here. I know angle alpha, and I know its opposite side 6. So I can set up the proportion. The sine of 35 over 6 is equal to the sine of beta divided by 8. Okay, I'm going to cross multiply. 8 times the sine of 35 is equal to 6 times the sine of beta. And I come back and divide both sides by 6. And that gives me that the sine of beta is equal to 8 times the sine of 35 divided by 6. But I don't want to know what the sine of beta is. I want to know what beta is. So we got to pull more information that we've already learned into this process. If I now take the arc sine of 8 times the sine of 35 over 6, that gives me angle beta. So that inverse sine function there. And when I put that into my calculator, I get that angle beta is approximately 49.9 degrees. Okay, now look. This angle, which is what angle beta is supposed to be, is not an acute angle. And 49.9 degrees is an acute angle. So if I take 180 degrees and subtract the 49, well, let me back up. What the angle beta actually is, the one we just found, we found this angle right here. That little angle right there is 49. Let me darken that pen. 49.9 degrees, which means this angle here is also 49.9 degrees because that's an isosceles triangle that we built. So let me stop there and point out that just from the little work I've done so far, I know that this is 49.9 degrees right there on that second triangle that I've got to solve. So if I take 180 degrees and subtract that 49.9 out, that's going to give me the angle beta that I thought I was solving for to begin with. So 180 minus 49.9 gives me 130.1. So this angle right in here is 130.1. This angle right here is the one I'm talking about, 130.1. Now I can actually find the pink triangle that I'm looking for, I can find the other angle because I've got two of the angles, and I know the interior angles of a triangle add up to 180. So if I do 180 minus 35 minus 130.1, I get that angle at the very top, angle gamma, is 14.9 degrees. So this is 14.9 degrees. So the only thing I'm missing in the pink triangle is side C, right here. I've got my side A, that's 6. I've got my side B. I've got all of my interior angles, so I just need side C. And I can use the law of sines because I've already got the angle and the opposite side relationship set up. So to find that side C for the pink triangle, let me just give myself a pink box to work in so that you know I'm doing this work for the pink triangle. I have the sine of 35 degrees divided by 6 has to equal the sine of 14.9 divided by side C. Let me stop here and just say, is everybody following where I am right now with this? This is a pretty involved case. Probably the most involved one that we're going to do all night. Okay, that's everybody. Awesome. All right, now I just cross multiply and do what I've done on the other triangles so far. So I've got C times the sine of 35 equals 6 times the sine of 14.9. I come back and divide both sides by the sine of 35. And I have C equals that expression. So C is equivalent to, when I put that into my calculator, I get that C is equivalent to 2.7. So now I know my side C is equal to 2.7. All right. Now I need to move to my other triangle. And don't forget, this other triangle that I'm solving for is this entire big triangle here. It's the whole thing. So I know my side 8. I know my side 6. I know my two angles, so I can figure out what gamma prime is by subtracting those out. So I have 180 minus 35, that's my angle alpha, minus 49.9, and the way I knew that beta prime was 49.9 is because of that isosceles triangle that I built. That gives me angle gamma prime as being 95.1 degrees. So now I know gamma prime is 95.1 degrees. So all I need now is side C, and we know how to do that. We use the law of sines. Okay, so I have the sine of 35 over 6 has to equal the sine of 95.1 over C, cross multiply, C times the sine of 35 is equal to 6 times the sine of 95.1. I'm going to come here and divide the sine of 35 off of both sides. And when I do so, I get that C is approximately, let's see, I ended up getting 10.4 there. So this is 10.4. And now I have the two cases solved for that could crop up with the given triangle information. Any questions about anything on the screen here? All right, green check if you're ready to move forward from this one. All right, good deal. Like I said, that one's the most complex one that we have to work through tonight, so everything else should seem like easy street from here on out. Okay, so we have another angle side-side case here, and I have a relationship set up of a known angle and its opposite side there. So I am going to go ahead and set up my law of sines. The sine of 85 degrees divided by 12 has to equal, we'll just start with beta, the sine of beta divided by 9. I cross multiply and get 12 times the sine of beta equals 9 times the sine of 85 degrees. And now I come back and divide 12 off of both sides. And I get the sine of beta equal to 9 times the sine of 85 degrees over 12, which means sine inverse of 9 times the sine of 85 degrees divided by 12 has to equal beta. And when I put that into my calculator, I get that beta is approximately 48.3 degrees. Okay. From here, so here's what I know. I know 48.3 degrees there. Now that I've got beta, I can figure out what alpha is. So 180 minus 85 minus 48.3 gives me a measurement of alpha to be 46.7. So this is 46.7 degrees there. And, pardon me, now we can set up our last proportion. The sine of 85 degrees over 12 has to be equivalent to the sine of 46.7 degrees over side A. Cross multiply, A times the sine of 85 degrees equals 12 times the sine of 46.7 degrees. And I'm going to divide the sine of 85 degrees off of both sides. And I get side A is approximately 8.8. And we are solved there. Okay, find all possible triangles if one side has a length 4 opposite of an angle 50 degrees, and a second side has a length of 10. Okay, so let's see. There's my 50-degree angle. And I have a second side that has a length of 10. And the side that is opposite my 50 is 4. Well, I don't know if that actually makes a triangle or not. It appears it's not going to. Either way, even if this was the side that was 10, because it just doesn't look like 4 is going to quite make it down there to 10, but we can actually use our law of sines to verify if it can happen or not. So let's start out with what we know. We've got one angle, and we do have its opposite side. So we can, and we'll call this alpha, and we'll call that side A. So we can set up our law of sines to potentially give us this angle right here, if it exists. I mean, obviously it's not going to because I keep talking about it. So I'll show you how it doesn't work out. Okay, so the sine of 50 degrees over 4 has got to be equal to, we'll call this angle beta, the sine of angle beta divided by 10. Okay, cross multiply. So 4 times the sine of beta equals 10 times the sine of 50 degrees. And I divide both sides by 4. And I get the sine of beta is, okay, so the sine of beta is approximately, when I actually get a number for that, I get 1.915. But if you did not stop there and realize something very important about what you just did here, say, okay, well, I don't want to know what the sine of beta is. I want to know what beta is. So you set up the inverse sine of 10 sine of 50 divided by 4. I want everybody to put that into their calculator and tell me what they got. What they get when they put that in their calculator. Okay, so all of the students that are in the room tonight keep saying, I keep getting an error when I'm putting this into my calculator. So here's why you keep getting an error. For one thing, this triangle doesn't exist. But the way you know that is the domain of sine, the sine function, sine of x, is -1 to 1. I'm sorry, I did not mean the domain. I meant the range. Remember, when it graphs as that wave that's oscillating between 1 and -1. And look, you said when I took the sine of this angle, I got 1.915. which lives outside of the range of the sine function. So that's why you keep getting what your calculator says is a domain error here. By the way, the domain of the inverse function is the range of the original function. So that's why it says domain error. So this can't happen. This does not exist. So there is no triangle with the given measurements. So I tricked y'all. All right. Let's go ahead and talk about area of a non-right triangle, and then we'll have one application problem, and then we're done. So we have the area, the formula for the area of a triangle, which is 1/2 base times height. And like we stated earlier, we always measure the height of a triangle from one of the vertices of the triangle perpendicularly down to the opposite side. So when we are dealing with oblique triangles, we have to have that measurement of the height. If you think back to geometry class years ago, you always had to be given the measurement of that height. So we have these cases here where the height of the triangle may fall inside the triangle, or it could fall to the outside of the triangle. So we've already figured out how to find the measurements of those heights. So this first formula, area equals 1/2 base times height, this goes with this first triangle because the base in that triangle is B, side B, and the height can be gotten by multiplying C times the sine of alpha. And that's from where we cross multiply and divide all that. So that's what we get when we do that particular calculation. So this other triangle with the height living outside, we have 1/2 base times height, and they're actually calling the base side A here to correspond with alpha, across from angle alpha. So we get that same formula for when the height lives outside of the triangle. And what it ends up doing is giving us these three formulas. So depending on what you're given, you'll either be given angle alpha, side B and side C. You'll either be given angle beta, side A and side C, or angle gamma, side A and side B. So notice, whatever angle measurement you're given, you're always given the two other sides that don't correspond to that angle. So that's how you can know which version to use. It's always 1/2 of your two other sides that are not opposite of your given angle times the sine of the given angle. Okay, so this is just a formula we're going to use to find the area of the triangle. And I could say a lot more about it, but for the sake of time, since we're almost up with our hour here, we'll just go ahead and use these formulas. And I've put them at the top corner there for you. So we have triangle with, I'm just going to draw a triangle here for us. We have a triangle, side A is 90, side B is 52, and we're given angle gamma, which is 102. And we want the area of this triangle. So since we're given side B, side A, and angle gamma, we're going to use this version of it. So the area of this particular triangle, we're going to use 1/2 A times B times the sine of gamma. That is 1/2 90 times 52 times the sine of 102. And when I put that into my calculator, super easy, I get that the area of that triangle is approximately 2289 units, because they didn't give me what we were measuring in units squared. Remember, area is squared. Okay? Any questions about that? These are really straightforward and easy. Just use your formula. Okay, it looks like everybody's good. We have one more of those to try. So this one, we're given angle beta as 42 degrees, and we're given side A, 7.2, and side C, 3.4. So this time we'll use the area is equal to 1/2 A times C times the sine of beta, which is 1/2 times 7.2 times 3.4 times the sine of 42 degrees. And I just put that into my calculator. And I get that the area is approximately 8.2. They told us we're working in feet, so feet squared, square feet. That's it. We've got one more problem, and it's a word problem. So find the altitude of the aircraft in the problem. So basically, you're finding the height of this oblique triangle. Notice you've got an angle, side, angle triangle that you're dealing with. Angle, side, angle. So we can use our law of sines. We actually have to use it twice, but it's no big deal. We can certainly figure out that, by the way, these are both 90-degree angles there. So the angle of this left-hand triangle there, that top angle, we'll call that gamma. Angle gamma there has to be equivalent to 180 minus 15 minus 90, because that corner makes a 90-degree angle there. And let's see, I actually didn't do that particular triangle. Let's see, 180 minus 15 minus 90, I get 75. That angle is 75 degrees. We can also know what the other one is too. Let's see, 180 minus 35 minus 90. 180 minus 35 minus 90 gives us 55. So this angle here is 55. Okay, so I can basically use either of my triangles. I need to know what side A is here so that I have at least one known angle, which is that 90-degree angle across from a known side. So I can use the big triangle and the 35-degree angle across from that to figure that out. Oh, and I need to know what this angle is put together, because I know that this entire side here is 20. So I need to know this entire angle so that I have that proportion to be able to set up, or that ratio so that I can set up my proportion. 75 plus 55 is 130. So we'll call this gamma prime is opposite, it's 130 and it's opposite the 20, the length that, I can't talk, the side that is 20 miles long. So I can set up the proportion of the sine of 130 over 20 has to be equivalent to the sine of 35 over side A. And if I can get side A, then all I have to do is focus on either of these smaller triangles to figure out what side H is. And I'll just use the bigger right-hand triangle, but you could use the smaller one as well. You'd have to figure out that other side, though, to be able to set up that proportion, and that would be more work. So we'll go with less work and use the left-hand triangle. Okay, so I'm just going to cross multiply here. A times the sine of 130 equals 20 times the sine of 35. And now I come back and divide the sine of 130 off of both sides. Those divide out. And I get my side A. Oops, I grabbed a white pen and y'all cannot see that. Side A is approximately 14.98 when I put that into my calculator. So 14.98. Okay, now I've got an angle that I know, 75 degrees. I've got, oh, no, wait, I don't know that opposite side because that entire other side is 20. Let me take that off. That's why I had to find side A. So here's what I know. Here's how I'm going to be able to set up that proportion. I know that this is 90 degrees right here, and I know its opposite side is 14.98. Okay, so if I can use the 15 degree side angle to find the height from the ground that the plane is. Okay, so I'm going to set that proportion up now. The sine of 90 degrees divided by 14.98 has to be equal to the sine of 15 degrees divided by my height. Okay, so this is really nice and neat because what is the sine of 90 degrees? You should know that off the top of your head by now. Think about your unit circle. Uh-oh. Nobody knows the sine of 90 degrees off the top of their head? Think about your unit circle, and we're talking about the y value. Yes, this whole numerator is just 1. So I can cross multiply now. 1 times h is h. H is equal to 14.98 times the sine of 15 degrees. Now, I did not have to convert that to 1. I could have left it as the sine of 90 degrees and divided it off both sides and you get the same thing, but this makes it a lot nice and neater. H is approximately 3.88, and that means the aircraft is at an altitude of approximately 3.88 miles. All right, that's all I have for y'all tonight. I hope that was helpful. I appreciate each. Okay, it said round to the nearest tenth, so it's 3.9 miles. Now I'm going to stop the recording.